Welcome guys, and welcome back to this second video for the lesson for the unit functions and equations. In this second video or second lesson, we will build on the discussion from the first video, and in particular we will address the following inquiry questions, skills and understanding. The first thing we want to do is to understand why we use symbols and notations in functions, and as a matter of fact in the whole of mathematics. Why do we use symbols and notation? Okay. The second thing we want to discuss is to understand what a set builder notation is. What is a set builder notation? SBN for set builder notation. So we will be discussing set builder notation as part of that first part, which is talking about symbols and notation. 3, we want to see how we actually use the set builder notations when we represent relations and functions, as we will see later. The fourth thing we want to do today is to understand what relation is, what is a relation, or what is a relation notation. So we will eventually understand that this is normally referred to as a function notation, but in this section we will be referring to it as a relation notation. Okay, so when we present a relation, we don't want to be using a graph all the time. We don't want to be using an ordered pair all the time. We don't want to use an equation all the time. So we don't want to use a table. So what is a relation notation? A short form of representing a relation. Okay. Number 5, why do the set builder notations differ for discrete and continuous relations? So we talked about discrete relations and we've talked about continuous relations. So when we represent these in set builder notation, the set builder notation looks a little different for discrete and for continuous function, and we want to see why. We will be able to understand why these are a bit different. The next thing there, which is the 6th point, is we want to express the domain, range, and range using the set builder notation. All right. So the first 5 points there you can see are questions, so they are inquiry questions, and the 6th and the 7th point are actually the skills and understanding areas or the content of what we are going to talk about. Okay, so to express the domain and range using set builder notation, and the 7th thing and last thing we are going to do is to use relation and function notation. Okay, we want to use relation and function notation to present different types of relation. Okay, so we will start with an opening problem there. What is this? So a particular relation. So this is building, remember, this is building on what we discussed in lesson 1. Okay, so keep that in mind. So a particular relation between two quantities x and y is given in the form of an equation. Remember, we can present a relation in terms of an equation, a graph, mapping, and all that, right? So this one is given in the form of an equation, which is given by that, and where x values are given as such, and it is to be presented in a mapping diagram. Okay, so the first question says list the elements in the domain and the elements in the range on a mapping diagram. So I'm hoping you remember what a mapping diagram is from lesson 1, and so here we go. So if we're going to represent this on a mapping diagram, we need to draw, first of all, 2 ovals, okay? One for the input, or the values of x, the other one for the values of y, okay? So put x there, input y there. We put in the values of the domain, which we have here, okay? -2, -1, 0, 1, 2, and I think 3, yes. All right, now we want to know what goes into y. Remember the values of x, the input determines what the output is, right? So the values of y are the output or the range or the dependent variable. So put in a value of -2 here, and if we put x is -2, so -2 here gives us +4 because the power there is even, so +4. +4 times 2 is 8. And 8 minus 5 is 3. So we expect that the output, if the input is 2, the output is 3, and we draw an arrow there to indicate the mapping of -2 into 3. Okay, we go to the next, -1, plug it in here. -1 squared is positive 1. +1 times 2 is +2. +2 minus 5 is -3. Maybe I need to do this just so that we are sure we get what's going on here. So we are plugging in x is -1. Okay, so if we put -1 there, remember we get 2 into -1 squared. The -1 has to be in bracket. So this square is for the negative and the 1. It's not just for the 1. And this is why we end up with, so this is -5. And so this -1, everything squared is +1 times 2 is 2. And so 2 minus 5, which will give us -3. Yes? And so that's how we end up with -3. And so when x is -1, the value of y is -3. And of course, we draw the arrow to indicate the mapping. Now we substitute 0. When x is 0, plug in 0 there. 0 squared is 0. 0 times 2 is 0. Minus 5, we end up with -5. So when x is 0, the value of y is going to be -5. And again, we draw the arrow to indicate the mapping. When x is 1, substitute 1 up there. 1 squared is 1, times 2 is 2, minus 5 is -3. We already have -3 here, so we don't have to write -3 again. And so for 1, we need -3. So we draw an arrow to indicate the mapping of value of x to -3, like that. Substitute in 2. Put 2 up there. 2 squared is 4. 4 times 2 is 8. 8 minus 5 is 3, which is also already in here. So we just need to draw an arrow from 2 to 3 to indicate the mapping of the input to the output. Okay, we are left with +3 for the input. If we put +3 up there, we get 9 here, 3 squared, times 2 is 18. 18 minus 5 should be 13. So we get 13 and draw an arrow to indicate the mapping. Okay, and so this is the mapping diagram as required by part A of this question. Okay, all right. What does part B say? I've decided to leave this here and put the part B there. So part B says, use a set builder notation to write down all the members of the range of the relation. So the question has to be, what is a set builder notation? And as a matter of fact, you've already seen it. What you see right here is a set builder notation for a discrete variable. So when we write, so this is for actually for the domain. So we can, by just looking at this, we can see that for the domain there, we can write that in set builder notation, the domain is expressed as x is an element of the set containing -2, -1, what was it? 0, 1, 2, and 3. So this is representing the domain in a set. So this, the 2 squiggly arrows indicate that this is a set. Okay, so that's how we represent the domain using a set builder notation. So this is a set builder notation for a discrete variable such as what we have here. So similarly, if we are going to put the set express the range in set builder notation, that means just write the range of this set is y values being elements of the set. What are that? We have -5. We usually start from the smallest, followed by -3, and then we have, I think it is 3 there, and we have 13. And this is the range of this particular relation, and we have represented the domain or presented the domain using set builder notation. Yes? Just as simple as that. So this is what we call a set builder notation. We will see that when we have a continuous relation, then we will present this just slightly different and for good reason. Okay? So I'll remove this before we move on. Okay, right, let's move on. So set builder notation for a discrete relation. So here I am defining what a set builder notation is. So consider the relation given as ordered pairs containing values of x and values of y like that. Okay, we can represent this ordered pair in a graph such as this. So this is 1 is to 4, 3 is to 6, 5 there is to 7, and 7 is to 10. Okay, so that's a set of ordered pair. The domain of this ordered pair must be the values of x, and then you put into a set notation those squiggly brackets, and we put the values of x. So we write x values are 1, 3, 5, and 7. And so that is a set builder notation for the domain of this discrete relation. Okay. Similarly, you can express the range of the discrete relation, and those are the values of y, again, 4, 6, 7, and 10 in a set like that. Excuse me. Okay, like that. Now let's define this. So the set builder notation for a continuous relation. So what's the difference between a continuous and a discrete relation? So the graph we had here, this is a graph of a discrete relation. Discrete because the values of x and values of y are distinct numbers. So we don't have all values here, we just have one value there, x is 1, and nothing else in between until we have 3, and nothing else in between until we have a 5 again. So they are countable numbers. Okay, counting numbers, that makes it a discrete relation. Okay, and now we want to see a set builder notation for a continuous relation. Okay, such a relation cannot be presented as a set of distinct ordered pairs as we've done in the previous case. And the reason is that a continuous relation, the domain has to be, because the values increase from some point all the way. So we represent in a graph, we represent it by a line. Okay, so instead the domain and range are presented in set builder notation as a range between two values. There's some beginning and some end. Okay, so some beginning A and some end B. We usually refer to this as the extremas. Okay, so for example, we can write x are elements of all real numbers lying between some starting point A, okay, to some ending point B. So anything in between can be a value of the domain. And similarly, the range can be represented in the same way. Okay, so set of all real numbers, you will need to remember that real numbers are really anything that is on the number line, whether it's decimal or whole number. including irrational numbers, can form part of the domain of a continuous function. Okay, so here's a graph of a continuous relation. Continuous meaning that all the points along the way are connected. So we can only draw a line between points in a continuous function and not in a discrete function. So if this is a continuous relation that starts from some point A to some point B, then what are the possible values of x? Well, anything in here, any value of x here is valid. Okay, so we can't say that x is 1, 2, 3. What about 1.1? What about 1.001 and so on? So all values along that range from A to B, the values of x are acceptable. All right, and so how do we show the domain here? Is anything, look at that, anything from A all the way to B. I hope you've seen what I've just shown there. So from A all the way to B is the domain. So all values of x along here will qualify as the domain. And when we present this, we write the domain as all values of x that are real and lie between -1 and 9. That means 1.1 is accepted, 2.05 is there, pi is in there, e 2.718 whatever is also in there. So all these values are accepted. Okay, all right. Similarly, the range of this distribution or this relation is from the minimum, the lowest possible value of y value, the lowest is here, and the highest possible value is up here, not at b, because there is, we can get a value of 7. B is slightly lower than 7. So when we are looking for the range, we are looking for the highest possible value of y for this domain here. And the highest possible value of y is at 7, somewhere up there. And so, as you can see, we can say that, there you see, okay, so that becomes the range, and we can represent that using a set builder notation and say y is all elements in the real set that lie between 3 and 7. I hope this has come out clearly, not just how to write the set builder notation, but also to be able to see what the range is by just looking on the graph like that. Okay? All right. Let's look at the question, some questions here. The mapping diagram R, so R for a mapping diagram or for a relation. A mapping diagram R is of the form R. So R here is for relation, okay? R is such that x becomes a times 2 power x plus b, okay? So we want to discuss a relation notation. So what you're seeing here is what we would refer to as a relation notation. By just looking at this diagram, pause the video and try to understand what this is really trying to say. A relation is such that x what into that. So it's kind of clear even by looking at this what that might mean, okay? So effectively what it's saying that the values of x will be mapped onto these values, okay? So it's similar to, really it's just similar to saying, it's similar to say, and if I write it like this, most of you will understand this immediately. This is similar to saying that r of x is a into 2 power x plus b. Okay, so you are familiar with this expression here. Normally we remove r and put f for function, as we will see later. So we are already ahead of the curve here, so it makes life much easier. So before we started writing like this, we used to write like this to say that a relation is such that all values of x are mapped onto this to give us a value of the output. So if we put in, if this is an input fed into the relation, we come up with something which is determined by this rule here, okay? Just like the previous case where we had y, where we solved for the range using some values of the domain, okay? So the mapping diagram R is of the form this. R of x is this. That is what it is saying, okay? Now what is the question? Okay, the spoiler alert there, take a look. So the spoiler alert is that this is something that you already are familiar with. In fact, we are ahead of the curve by a margin. We shall later discuss the function notation, what I just did there, okay, where we will simply replace this R here with the letter F, which you are familiar with, okay? All right, and let's move on. So what is this about? Move that to the side. And part A of the question is asking us now to list the elements in the domain and in the range of R using the set builder notation. So what are the values in the domain? We want to use set builder notation to express the domain and to express the range. Okay, so how do we express the domain here? We already have our domain except something is missing there. Before we can express our domain, we need to know what this G here is. Okay, we could we could move on without the G and leave it there until the end, because there is a part B and a part C of the question. So let's just say we will put it temporarily at G. So we can write that the domain, I'll write here domain, the domain is X. This is a discrete relation, so I just need to put that, and then I can put 0. Is that -2, 1, -1, and G. So this is the domain using the set builder notation. This is a G, not 9. Okay, and what about the range? Okay, so the range, in the same way, we can express the range as y values are elements of the set -1, comma, -1.75, comma, 0, comma, -1.5, comma, and I think the last one there is 30, and that is the range expressed in set builder notation. It's as simple as that, right? But this calls for some of the stuff that you have learned before. The next part requires us to remember stuff that we've done earlier. Last semester, I think. Let's just see what we have. So that is pretty straightforward so far. No big deal, really. And that one. Okay, what's the next part asking us to do? The next part is for us to find A and B. So now look at this. This is saying R is such that X becomes A times 2 power X plus B. So if you see look at this clearly, this is an exponential function. So put a value of X in there and you get a value of Y. Now we can make use of our mapping here to help us find the values of A and B. And how do we do that? We pick carefully some numbers that will make our life very, very easy. Like if I have X is 0 and if I have X is 1, life becomes very easy. So for example, for X value equals 0, if we substitute, I should get a Y value, which is -1. Okay, so if I put this 0 into this function, whatever I get should be the value of Y that is here, just like we did with the first question, okay, the opening problem. So when x is 0, plug in 0 here, we get a times 2 to the power of 0, okay? And then we add b. 2 to the power of 0, and this thing here must be equal to negative 1, okay? So 2 power 0 is 1, so we have a plus b equals negative 1. I hope you are understanding this. Okay, I'll call that my equation 1. Okay, we have two unknowns, so one equation cannot help me. Now I pick another point. I can pick negative 2, but look at the result. It's just going to complicate matters. I want stuff that is easy to simplify, so I'm going to take 1. Okay, so when x equals 1, then I have a, okay, into 2 power 1 plus b must be equal to 0. If I simplify this, I get 2a, this is 2a, 2 power 1 is 2, times a is 2a, plus b equals 0. So b must be equal to negative 2a, which is my equation 2 now. All right. Now, if I substitute 2 into 1, this is a simultaneous equation. You can solve it any way you like. The best way here, just make b the subject of equation 2 and plug it in here. Where there is b, remove and put negative 2a, and I get a minus 2a is negative 1. Negative a minus 2a is negative a, must be negative 1, must be equal to negative 1, and so a has to be equal to 1. So I know my value of a now. Yes, take a moment and take a look and be sure that you understand what I've just done there. Okay, we've taken values of x from the input, from the domain, plug into the relation, okay, equation there, and find the values of y, and that value of y must be these ones here. Okay, so that's what we've done for values of x of 0 and a value of x of 1. We could try with others as well. Should give us the correct answer. It's just you're working with the decimal, so it's going to take you longer and you might make an error. So always you choose the easiest path possible. Now that we know the value of a, we can also find the value of b. We can find the value of b by simply plugging that back in. We can put it right here. A is 1, so plug it right there. We can see that b is the same as what? Negative 2. This is the value of b. Okay, take a, put it in here, or you can also put it here. A is 1, so if you take it to the other side, it becomes negative. So negative 1 minus 1 is negative 2. B is negative 2. Okay, that means I can simply write this thing now as R is such that, so this means is such that x values maps onto a is 1, so I just ignore it and put 2 power x plus b, but b is negative 2, so minus 2. So that relation can actually be just expressed like this. Okay, that's that. The last part of the question, I'm going to go to the next question and leave this here. Let's hope it doesn't interfere with it so that we can make use of these results directly. It's asking us, I think, to find the value of g there. Okay, so part C, hence find the value of g. Okay, so it means when we substitute g into the function, so let x be g. So if x is g, then that means it's g we are substituting here. So 2 power g minus 2 must be the output there, which is 30. So when we put in g, we expect to get 30 there. So this must be equal to 30. So 2 power g, can you still see? Yes. So 2 power g must be 32. What number is that? This must be 2 to the power of 5. And so, clearly, your value of g has to be 5. And now that you know the value of g, you can put it back into the original question that was asking you to write the domain and the range of the relation. Okay, so this is how you handle a question like this. This was actually a question in the IB exam for math studies. I think it was math studies. There's another one similar to this I've seen for math SL. Who knows, maybe you will meet it one of these days soon. Okay, so questions like this, if you look at this, by the way, you should notice that it's really nothing different from what you've done before. Okay, as I told you before, we've kind of short-circuited this. We started with tougher things before we got into this, so it should be much easier to understand now with your prior knowledge. Okay, if you didn't get it, just let me know and we can discuss it again. Right, we'll move on to the next. So we can use ordered pairs, we can use a mapping relation such as this one, okay, to find unknowns in the same way that we do them with functions. Okay, let's move on. So we are done with that. We move on to slide number 6. So if a relation R is such that, so this is now like a formal definition of a relation notation. So if a relation R is such that the set of all members of the domain, that means all the values of x, remember the set of x's, x values, map onto the set of y values. Mapping onto is an arrow with some line on at the end, right? So if all the values of x maps onto a value of y, then by set builder notation, we write R. So we read this as R, this means is such that x maps onto y. Okay? We could write this like this. We could simply write R of x is y. That is what it means. Okay? Same thing that you have seen before. R of x is y. Okay? That's what this thing really means. So, but when we write it in a set builder notation, as in the mapping notation like this, it kind of has a leading meaning, which is to say it's telling us that for this relation, all values of x map onto the value of y, or by putting in a value of x, you get an output value of y. Okay? So the y is usually expressed as a relation equation. So in place of just putting y, we normally put a relation equation such as we did in the previous question here, like that. So instead of putting x and then putting y here, so in place of y, you put the relation equation. So this is y equals a into 2 power x plus b. So in place of putting y, you put the equation that relates the two, okay? So the y is usually expressed as a relation equation. For example, if you remember in lesson 1, for the fuel to distance relation for the car that we were talking about, I think we found y was equal to 12.5x, which means that if I put 1 liter in the car, it could take me 12.5 kilometers. And if I put 10 liters, it would take me 125 kilometers, and so on. So this was the relation equation. So if I wanted to represent this in a relation notation, I would write, I think I've shown this, let me just go ahead. So in a relation, we would write something like this. So the relation for the motion of this car, fuel versus distance relation, would be that the number of liters maps onto the number of kilometers I can travel. So that is what the relation notation looks like. Eventually, like I said, we will be referring to this as the function notation once we know what a function really is. Okay, here is another question. This is for you to recall some symbols. Okay, just in case you thought you had escaped this, there is no escape of this until all the way to DP2. Already you started seeing this stuff previously when we were talking about the real numbers and so on. Okay, complete the table below by placing a tick. This was also an IB question. By placing a tick in the appropriate box if the number is an element of the set, and a cross if it is not. So if it's not an element, you put a cross. If it is an element, you put a tick. Okay. All right. Let's see. So we have a diagram there. Okay. Let's start with 2. Does 2 belong to the set? This set here. This is a set of natural numbers. Natural numbers are also called the counting numbers. So does 2 belong in the set of counting numbers? And the answer is, of course, yes. 2 is a counting number. 1, 2, 3, 4. So 2 is definitely in this set. We put a tick there. Does 2 belong to the set of, what is that there? Pause the video if you want to think about it. Well, this is the symbol for integers, okay? So does 2 belong in the set of integers? Yes, 2 is definitely an integer, okay? Whole numbers, or whole numbers, right? Positive or negative are referred to as integers. It's kind of wrong to say whole numbers because the word whole numbers also has its own distinct meaning. What about Q? What does Q mean? Pause the video and remind yourself of what Q means. Okay? Q from the word quotient is rational number, that you can write the number as A divided by B. Okay? So if we can we write 2 as some whole number? Can we write it as some whole number A divided by some other whole number B? And the answer is yes, provided B is not 0. Yes, we can. We can write it as 2 over 1. Okay, so 2, therefore, is a rational number, and we can put a tick there. Is 2 a real number? Yes, 2 is a real number. All numbers in the number line are real numbers. All of them, decimals and non-decimals and rational and irrational numbers, including pi and e, all those are real numbers. We go to root 3. Is root 3 a counting number? Well, root 3 is not used for counting. There is no counting the number of dogs in the park and saying 1, 2, root 3, root 5. There is no root 3 is 1.372 blah blah blah, yeah, and it is a non-ending. It's an irrational number, so it does not fall in this set. So here for root 3 is not a natural number. It's not a counting number. Is root 3 an integer? No, root 3 is not an integer. Integers, when we say integers, we are referring to -3, -2, -1, 0, 1, 2, 3. Okay, these are the integers, positive and negative numbers like that, including 0. They're on the number line, but they are whole size, not decimal. Those are the integers. So root 3 is definitely not one of them. Okay. What about Q? Is can root 3 be expressed as a fraction of whole numbers? Actually, no, we cannot. Root 3 is 1.732 and so on, and it's an unending, non-terminating decimal number, and therefore, because it is non-terminating and it's not recurring decimal, we cannot express it as a fraction, and therefore it is an irrational number. It is not a rational number. Is it a real number? Yes, it is a real number. it can be found on the number line. So it is a real number. So yes, root 3 is a real number. We go to the third one. There is minus 2 over 3 a counting number? By definition of what we said, counting numbers are we start counting by saying 1, 2, 3, 4. We don't even go to 0 and we don't go into the negative. So has to be positive numbers and they must be whole. Okay? So minus is already a flop, and again it is a fraction, 0.666 recurring. That means it cannot be a counting number. So this one flops the natural number line status. Is it an integer? Once again, no. We've explained what an integer is, these ones and the negative ones. Okay, so it is not an integer. Is it a rational number? Can it be expressed as an integer over an integer? And the answer is yes. So it is, in fact, a rational number. Is it a real number? All numbers in the number line are real numbers. And therefore, this is the result of what we would expect you to do for a question like this. All right, let's move on. So that was that. Part A. There is a part B to this question, which should be more interesting. That was just a reminder of stuff that you need to know, because when we do set builder notation and what we call relation notations, we will need to be able to use these symbols for the number sets, special number sets. Okay. Part B. A relation R is given by, here is a relation notation there, and a set builder notation for the domain is also given. Draw a mapping diagram to illustrate this relation. Part B, part 2, write down the range of the relation. So first of all, draw a mapping diagram to, we draw a mapping diagram for this relation. So a mapping diagram would have a mapping diagram. We put two ovals there. There's one there and another one. And this is going to be the values of x, these values of x here. And the values of y are determined by that equation there. Okay, or that, sometimes just say that rule. Okay, so the values of x are -2, 2, and 3. That's it. Okay, so we want to find out the values of y. When x is -2, what's y? Plug in -2 there, we get +4. So what we have here, it is 2 there into -2 squared. Okay, and then we're going to say -3 into -2. If you work this out, this is +4. That makes it 8. 8 plus 6. Because this multiplies that and turns it into a positive. So we expect the answer there to be +14. Look at it carefully so that you see what we've done. So this is +14. Yeah. +14. The next one there is 2. So plug in 2 here. If we plug in 2 in the same spot, I don't like that, making the place look filthy. So plug in 2 here, we get 4 times 2 is 8, but now this is +2, so this becomes -6. So 8 minus 6, which is 2, and so the y value there is 2. Plug in the value of 3. Okay, 3 here is 9 times 2 is 18. 18 minus 9 is going to be 9. So this is the, are we done? No, we are not. We haven't drawn the arrows that complete the mapping. So we say that 2 maps onto 14, minus 2, and 2 maps onto 2, and 3 maps onto 9, like that. We now have a complete mapping diagram for this relation, for relation R. Write down the range of R using obviously the set builder notation, and we would say the range contains the values of R such that Y values are, put the set there, and you say 2, 9, and 14, like that. And that is the range expressed in set builder notation. Okay. Next question, or next point. Next point, discussion. Okay, so we've done the range. Okay, so now we have problem set. We'll do a few, and then some of it I want you to do for me. So for each of the graphs, so if effectively we are done with what we wanted to learn today, effectively knowing what the set builder notation is, the set builder notation for expressing the domain and the range, okay? Writing a domain or range in set builder notation. And the second thing I wanted you to know is how to make use of the relations notation, okay? Which we've also looked at. We've actually used it to solve some and find some unknowns, okay? So for each of the graphs of relations that are going to be shown here, use the set builder notation to write the domain and the range of the relation. So you're going to write the domain and range using set builder notation, okay, just practicing that. And B, you will state whether the relation is discrete or continuous. And in part C, you will write a relation notation for whatever you see here. So let's, we will use this as an example. I will leave you with some to do yourself. So here is one relation there, okay? I am not very sure about, most students will usually have done part of this in MYP, IGCSE lower classes. When you see a circle that is unfilled at one end like that and one that is completely filled like this, there is a meaning, okay? So this usually means that we are starting from that point, but that point is not included. So if I drew on a number line like this, if I came and drew something here like this, okay, and I draw, that's an incomplete circle, and I draw one here that is completely filled up, okay, and I'm told that this is a function or this is a relation, and you're told to write down the domain of this relation, we will say this is all x values. The domain contains all x values starting from, this is 3 here, so starting from 3, okay, and ending at 5 on this side, okay? The circle means that we cannot include 3. So we are taking all values starting from 3 to 5, except 3 itself is not included. So greater than 3, not greater than or equal to, and less than or equal to 5. So if the end is completely filled like that, that means it is included in the range. If that is left at a circle like that, it means it's not part of the domain. So 3.001 is included, 3 point anything above 3 is included except 3 itself. So 3 is not part of that domain. Okay, so that's what that these two really mean. Yeah, most of us usually do that a little earlier, but just in case you haven't done that before, that is to remind you of that. Now, the question here is for us to state the domain and the range. Now, if you remember the first graph that I showed you, okay, we can see that the domain is, the lowest possible x value on the graph to the highest possible x value on the graph. And if you look at this, you should see that the lowest possible x value has to be greater than, okay? So -5 is our boundary, but it's not included. So if we were going to write the domain, we would say the domain there, the domain is all values of x, okay, that are real, because this is a line, meaning it is continuous. I've already answered part B there. It is continuous such that x values are greater than -5, not greater than or equal to, greater than because that's not filled, and we say less than or equal to, and what value is there? 5. And because this is a set builder notation, we now have a bracket there and a bracket there. Notice how this is a bit different from what we did for discrete functions. So for discrete function, we just said x is an element of, and we put these brackets here and filled in some whole numbers in there. Okay, that was the case for a discrete relation. Whole numbers with commas in between, -2, 3, 7, like that. So this is how we represent discrete relation. This is the set builder notation for a discrete relation, and this is the set builder notation for a continuous function. So we have to state whether the values of x are real or not, because they may not be real, right? They are real, and we can't say -5 -4 because -5.1, or I mean -4.9 is in there, -3, 0.0001 is in there. So we take a range of possible values, and this is how we represent it. Okay, there's another way of representing this, but we can talk about that later. Well, I think we leave that for a moment so that we get used to this first, and then we can look at other alternative methods of representing this. Yeah? And so that's the domain. That's the domain of this particular relation. That's how we would represent the domain. Okay. What is the range? The range must be from the lowest possible value of y you can see there to the highest possible value of y you can see there. So look across and see how much is that? How much is the lowest point there? So check the lowest point here, okay, and check the highest point up there, and that distance that is going to form the range. So if we check carefully, we can see although here the y value here is -2, but we can't take that because it's not included. However, this is included, okay, and this is also included. So although this is not included, this cannot help us. This is still on -2, and because this one and this range here, this region here, and this point here are valid, we can say that the range of this relation contains values of y such that y values are also real, okay, and y values lie between -2 but inclusive, so greater than or equal to -2, and the highest possible value is +2 up there from what you can see. So we can say less than or equal to +2, like that. And that is the set builder. That's the set builder notation. I mean the range expressed in set builder notation. I want you to just get good at this. It's really simple like that. But you will see other questions where it might start to confuse you a little, but eventually you get the hang of it. Okay, so it's this straightforward. Let's look at Another one. What else is there? Write a relation notation. So we've done, because we are expressing like this, and because you can see that the points are joined by complete lines like that, this relation is actually continuous and not discrete. Okay? The next bit is for us to write the relation notation. Now, this calls for a bit of our understanding of gradients of lines, straight line graphs. Because what you see there are straight line graphs, and we need the law or the rules for each part of the line. Okay? If you remember the equation of a line, so hopefully we can do this quickly. The equation of a line is given by, I'll write this here, the equation of a line is given by y equals mx plus c, where m is the gradient and c is the y-intercept. So what we need to do is to find the equation of each section of the line. This should be straightforward. We can see that this line passes through this point here. This point is -5, -2, and we can pick another point, let's say here, and that point is -3, 2. So this point here is -3, 2. We can use that directly to find the equation of the line by looking for the gradient. What's the gradient of that line? The gradient is m is y2 minus y1. So y2 is 2, this one here. Subtract this, minus -2, that is 4, over x2 minus 3 minus -5. I think this is -5, right? And so what we have, 4 over 2, which is 2. So the gradient is 2. We could easily have got that by just saying here there are 4 steps, change in y is 4 steps, and change in x is 2 steps. So 4 for every 2, so the gradient is 2. So we know the equation of this line has to be y is 2x. Since the gradient is 2, we know the equation of this line must be y is 2x plus some constant c. And how do we get that constant c? We take one of those values, which was -3, I think it was -3, 2, and plug it right in there. If we put this here, we get 2 here. So we get 2, yeah, for value of y equals -3, or 2 times 3. Sorry, that's terrible. Okay, so the gradient is 2 and x is -3, so that's -6 plus c. So -6 put to the other side becomes 6 plus 2 is 8, so c is 8. So this is 8. That is the equation of this line here. Okay, what's the equation of this line? That's straightforward. The equation of this line is line y is 2. Horizontal line, y is 2. What's the equation of this line here? You can see that the gradient is -1/2. Okay, -2. Change in y, okay, is -4 divided by 2. So the gradient of this line is -2, but the line is passing through the point 2 on the y-axis. So the equation of this line is straight away y is -2x plus 2. That's much easier. This one, the line is, this is -2 here, and it is horizontal. So the equation of this line is y is -2. The equation of this line, the gradient is definitely 2 because 2 over 1. So the gradient is 2, okay, and it's passing through the point. So the gradient of this line here, let's call this line 1. This one is line 1 here, okay. Let this be line 2. Let this one here be line 3. Let this be line 4. Okay, this is line 5. whose gradient we want to find. Gradient we already know. This is line 5. We know the gradient is 2. This is line 6. The last one is line 6. Okay, so for line 5, the gradient is 2, so we know the equation is y is 2x plus c. We need to find c. Okay, so we know the line passes through 4, 0. So it's passing through 4, 0 there. So x is 4, y is 0. 0 is 2 into 4 plus c. So c is negative 8. So the equation of this line here is y is 2x minus 8. That is for line 5. Okay, so for line 6, same thing, gradient is negative. Okay, and I suppose it's going to pass through positive 8 if I, okay, so anyway, so the line 6 is y is negative 2, gradient is minus 2 by the same reasoning, plus some c. It's also passing through 4, 0, so 0 is minus 2 into 4 plus c, so this is negative 8, goes to the other side and becomes positive 8. So the equation of line 6 is y is minus 2x plus 8, like that. So we know the equation of all the lines. We need those equations to be able to do this, okay? So here then is the relation function for this. So we write R is such that x maps into, and then we draw this like that. And we say the first one is 2x plus 8, comma, and this applies for values of x less than, greater than negative 5 and less than or equal to negative 3. So we say this is true for negative 5 is less than x is less than or equal to 2, like that. Okay? Or it is, the value of it is just 2, the value of y is just 2, the value of y or x maps onto 2, but this, it's exactly 2 for values of x lying from minus 3 to 0. From minus 3 is less than or equal to x is less than or equal to 0. Like that. Okay? Normally we would, because we've included this, we would do that. Was it? This is supposed to be, was it up to negative 2? Yes. And this is negative, is that negative 2 or negative 3? Minus 5 to minus 3. So this is minus 3 here, not minus 2. This here is negative 3. Because we've taken that there, we remove this from here. And we have negative 3 to 0. And then the next one, after this one, line 2, we go to line 3, whose equation is minus 2x. And what is it? Minus 2x, I think it is plus 2. Plus 2. And that is true for between 0 and 2. So we write for 0 is less than x is less than or equal to 2. Okay, we've done that. We are left with 3 to go. This is line minus 2. For values of x is from, for values of x from 2, less than x, less than, and I think that is just 3, less than or equal to 3. 2 more to go. The next one there is line 5, which is this one here. We say 2x minus 8. You can still see that? Yes. Is, so this starts from line 5, 3 to 4. 3 is less than x is less than or equal to 4. And then the last one, I'll just write it here. It's supposed to be down there. There's not enough space. So we would just write minus 2x. That can't be seen. Can write it here. Minus 2x. And it is plus 8 for values of x lying between 4 is less than x is less than or equal to 5. And this is how you would write down a relation notation for this function. Okay? this is sometimes referred to as a piecewise function. When it is a piecewise function, when you represent it, you do something like this, because each part, each piece of the function has its own independent equation. So you have to do this and say the function has the rule this for between this value of x and that value of x. It has a rule, this one, for this range of values of x. So the rule that is being used differs for different parts of the graph. So that's why we refer to this as a piecewise function. It has different pieces within itself. Okay? That's why. I hope that wasn't so complicated. If you've forgotten how to do your equations, finding equation of a straight line, well, you have an opportunity there to play this slowly and see how we are getting those equations. I hope this was helpful. Okay? You can move aside. So you pause the video and take a look at what we've done. Just be sure you can follow through on something similar. Like I always say, all the different parts of mathematics somehow relate to one another. You can see we are in a completely different topic, but we are still going back to talk about equations of straight line. We are still going back to talk about the special set notations, symbols, and so on. Right? We are still going back into exponential equations and exponential functions, and we are in a completely different area. So it's not exactly completely different because all of these areas are interrelated. Okay, one part relates to the next. So you cannot afford to forget any area, and the best way to do so is to continually practice. Okay, look at practice questions from past papers and so on, or ask for our question bank, and I can always get you more. All right, this is a second one. Let's see. Here's another one. Okay, the domain and the range. I'm going to let you do this one. So look at it carefully. Okay, you have different points. You have to look carefully to see. Hopefully you can see the grid. I intentionally made it darker so that doesn't interfere. There's no too much reflection. So hopefully you can see the grid lines. This is -4, -3, 1, -2, 0, and so on. So with that, can you do a set builder notation? Can you decide, excuse me, decide whether it is a discrete or a continuous